Good morning, good afternoon, good evening, folks. Welcome to another FCIA educational series seminar webcast. Today, we're going to talk about benefits of Fibre Channel running over NVMe for containerized machine learning models. Okay, so this is a very interesting topic, very contemporary topic. You know, all the talk about AI and ML. And today, the team is going to be talking to you and helping you understand how to run these type of workloads on a Fibre Channel protocol. So we have a great set of presenters today. Starting with Ramya Krishnamurthy. She's a very senior architect at HPE, and she works on a primary storage platforms. Ramya has been with the company a long time, and she has about 20 years of experience in the storage domain. Nishant Lodha joins us from Marvell. He's a senior technologist, and you've heard from him multiple times. So he has some great content to share again today. And we have three more engineers joining from HPE Bangalore, starting with Ajay Kumar. Ajay is an expert technologist, and he has over 15 years of experience in servers and storage. Also, we have Ashish Neekhra. He has also worked on different server storage and virtualization technologies. He's also a very senior specialist and over 15 years of experience. And then we have a new engineer at HP, Namrata. She's been with the company for 2 years, and she has a lot of knowledge in machine learning, and she's working in our QA department. So that's a great set of speakers we have today. I'm looking forward to the presentation. FCIA, as you guys know, we do this on a regular basis. FCIA is a nonprofit, and basically it's an industry association consisting of all companies that are working on Fibre Channel. So you're welcome to join FCIA, and it's a very interesting group of people, and everybody benefits from it. So the FCI organization has been, in existence for more than 25 years. We have some of the most industry-leading companies as members. And as you all know, Fibre Channel is still the #1 protocol for storage transport, and we have over 150 million Fibre Channel ports that we have shipped. Today's agenda is very interesting. So some of you, you'll learn some new stuff. I mean, we'll talk about containers, how containers are deployed and what the importance of containers is in machine learning environment. We'll also go through the fundamentals of machine learning. What are the different vectors? What's the workflow? So, some folks will really benefit from this content. In terms of storage, we'll talk about what are the requirements in terms of machine learning and what's the architecture that are deployed with customers. And we'll also talk about FC-NVMe, what are the advantages of this architecture, and then specifically, what are the advantages of FC-NVMe running machine learning workloads. So very contemporary workload running on Fibre Channel network. So it's will be cool to see that. And then we'll also talk about the solution. How we ran the solution, and then of course we'll show you some numbers, showing some performance advantages, and then close it out with summary. Please feel free to post your questions on the chat, and we will try to answer them at the end of the presentation. So feel free to put those questions in, and we already have received some questions in advance. Okay. Now I'm going to hand this over to Ashish. Ashish, please go ahead.
Yeah, thanks, Rupin. Hello, everyone. So in this slide, I will provide you a quick overview of what the containers are and how the containers work with Docker. The containers are nothing but a form of operating system virtualization that allows us to package an application and its dependencies together in a single portable image. Each container runs on isolated environment, which means that the containers can run different version of operating system libraries and can have different configurations. So if you see, Docker is nothing but the container management tool, which offers a portable, flexible, and efficient way to package, distribute, and run application, making it easier to develop, test, and deploy software in modern dynamic computing environments. Let's see how Docker containers differ from VM. So we have a pictorial view that talks about the advantages of container. Container shares the same OS kernel, eliminating the need for a separate OS for each application and is much smaller in size. Often only a few megabytes, resulting in increased service efficiency. Virtual machines, on the other hand, demands a separate OS installation, and each VM is isolated from the host and the other VMs, meaning that each VM has its own file system, network, CPU, and memory resources. So this frequently means that container may start in a matter of seconds versus the gigabytes and minutes required for a typical VM to get boot up. Uh, Containers are lightweight, immutable, stateless, and predictable, and provide several advantages that traditional systems may not offer, like version control and cleaner upgrades. These are the two examples of that. Uh, there are a few of these reasons why containers make it easier to deploy, patch, and scale application quickly. In case if you are more interested in knowing about containers and its open source container orchestration tool Kubernetes, which is used for automating software deployment, scaling, and management, we have attached a webcast link for the same in the slide. So moving to the next slide. Yeah, let's talk about why we need containerized machine learning models and importance of Docker in machine learning. So machine learning software is part of a larger ecosystem that includes numerous projects and contributors. As a result, dealing with issues like consistency, portability, and dependency management, it is difficult. And this is where container technologies comes in. To add more details, machine learning models can use up to a lot of resources. Thus, they need a lot of processing power to predict, validate, and to adjust themselves several times. Training large ML models repeatedly on a standalone system adds complexity and might cause the machine to slow down, or you can say it can become unstable since it consumes local resources for an extended period of time. However, implementing the same machine learning model on containers improves consistency, then portability and dependency management, allowing us to optimize resource allocation in a clustered environment utilizing various container orchestration tools. The other thing is reproducibility. Since ML is an iterative process that involves a lot of trial and error, including the testing and use of new algorithm, as well as validation. Managing this can be greatly added by containerizing the ML model. Containerizing provides a consistent environment for model training and deployment, making it easier to reproduce results and avoid bugs caused by the differences in software and library versions. Due to this portability, it is also simple to share your container. You can distribute it as a container image or as a container file. Since container can be run on any system that supports the Docker runtime, it makes it easy to move your ML application from development to production or from one cloud environment to another. With containers, both collaboration and scaling on a cluster becomes much easier. The diagram here, it shows us an understanding of how containerized ML model works. ML models are packaged as a Docker image with all of their dependencies, and containers can be launched from their supported container orchestration engine, such as Kubernetes. Also, container are used in various important stages of ML, such as data collection, pre-processing, training models, prediction, application deployment, and operational stage where we monitor ML models for errors, crashes, and latency. With this, I'm handing over to Ajay to cover more on ML fundamentals. Over to you, Ajay.
Thanks, Ashish. Yeah. Uh, Moving on to the next slide. So we'll do a quick overview of the machine learning. So, in simple terms, machine learning is an artificial intelligence application that allows systems to automatically learn and improve from experience without being explicitly programmed. It helps to identify patterns and make decisions with minimal human interventions. This being also used by businesses in almost every area to stay competitive. All businesses relies on data to operate. Decisions based on data are becoming increasingly important in terms of staying competitive or falling further behind. Machine learning enable organizations to identify profitable opportunities and potential risks more quickly. Machine learning has the potential to unleash the value of corporate and consumer data while also enabling companies to make decisions that keep them ahead of the competitions. Hence, ML is the foundational feature of business decision making. So let's talk more about machine learning algorithms. Machine learning is the study and creation of algorithm that becomes better at a specific task when they receive more data about that task. There are numerous benefits to collecting more data or data on a regular basis because it allows us to keep track of previous events and use data analysis to uncover recurring patterns. Most machine learning models begin with training data such as large group of emails or a huge folder of images, which the machine processes and begins to understand statistically. However, we can't fit and evaluate machine learning algorithms on raw data. Instead, we must alter the data or pre-process it, clean it to meet the needs of algorithms. Furthermore, we must choose the right data format in order to get the maximum performance on a predictive modeling project. Once we have a recurring pattern, we build a predictive models using machine learning algorithms that looks for trends and predict future changes. As shown in this diagram, data is collected and pre-processed before being trained using an ML algorithm to build the model. The patterns discovered are used to predict the outcomes. ML algorithms are categorized as either supervised, unsupervised, or reinforced learning algorithms. The process of understanding the data is critical in selecting the right algorithm for the right problem. Furthermore, machine learning can be divided into traditional ML and deep learning. As we all know, some algorithms can work with a smaller sample set while other requires massive amount of data. So traditional ML works well with less data and a deep learning system requires a large data set to eliminate fluctuations and make high quality interpretations due to its complex multi-layer structure. As a result, with deep learning, we get better performance with more the data. Machine learning also helps businesses to take decision in a time efficient and well structured manner. It helps in a different analytics depending upon the amount and type of data like decision making, predictive analytics. Hence, categorizing the problem and understanding the data is critical in determining the algorithms to implement in a reasonable amount of time. So with this, I'll hand it over to Nishant. He will talk more about the stories in machine learning.
Hey, thank you, Ajay, and thank you, Ashish. Well, we've all kind of heard of these concepts, whether it's containers, Kubernetes, or machine learning, deep learning. It's kind of good to hear from you guys who have direct experience in this and what you think about that. I guess need to advance my slides. So my name is Nishant, and what I want to do is take what Ajay and Ashish spoke about and put it in the context of storage, right? Because we need to kind of start thinking about how storage plays such a critical role in the success of machine learning and deep learning workloads, and what are the kind of current challenges and how can we solve them? So just to set the kind of picture clear, right? When you think of machine learning, or more specifically, most deep learning infrastructure, the things that you spend your kind of capex or opex on, right? They involve a bunch of things. Although most of the time, the conversation between people kind of deploying machine learning infrastructure is about GPUs, right? But there is kind of more to that, and while definitely kind of GPUs by many estimates are one of the most expensive from a capex perspective component of a for machine learning infrastructure, there are other things that play a significant role, and there's definitely storage, which is primarily NVMe storage. In many kind of reference architectures for machine learning, the storage is typically captive to the server. If you have kind of looked at the NVIDIA DGX architectures, which many other machine learning nodes are built from, right? And which was the kind of the traditional model for machine learning, where most of the storage was definitely NVMe, anywhere up to like 4+ terabytes or greater per node of NVMe storage. But it was pretty much captive. But that is changing because as machine learning kind of workloads have grown in terms of significance, in terms of where they are deployed, in terms of their impact to kind of business applications and business decisions. It has become imperative to kind of look at storage one more time and figure out whether we need the efficiencies that external disaggregated storage brings to these machine learning infrastructure. And that's where storage fabrics have started to become important, where you disaggregate some of your storage into external storage and then kind of use one of the known and trusted protocols, whether it is Fibre Channel or RDMA or any such thing, to go access that storage, right? Now we already know that when these machine learning clusters talk to each other, typically you need n number of GPUs to get your work done, and you just can't fit all of them in a single server, and eventually need to scale out to multiple different deep learning machine learning nodes, and you need RDMA, and more specifically RockV2, to kind of cluster you between the nodes. And I'm not saying that's the only option. That's kind of one popular option that's used. But then there is also Fibre Channel that provides you the similar model that RDMA does, which is kind of connecting all your GPUs together, where RDMA provides Fibre Channel provides a model where it connects all your storage together, right? And help you build this beautiful pool of storage that you can use across the different life cycles of machine learning. And then certainly, both Ashish and Ajay talked about the containers, the need to scale this across infrastructure, across data centers, across public and private cloud. And so you definitely need the software. And we all know, and perhaps when Ramya comes on, she'll talk about some of the workloads that the HP team did to characterize the performance of Fibre Channel for some machine learning workloads. But the stacks, whether it is TensorFlow and PyTorch, they play a critical role in the success of machine learning. But the point that I want to make, and for what I want you guys to kind of walk away with, is that often storage and access to storage is an afterthought for many different at least in my visibility, the architectures that I have seen, especially the on-prem architectures that I have seen, they're often kind of constrained on storage and storage accesses. And I often equate that to keeping a $500 an hour lawyer waiting in the lobby. You don't want to do that. These GPUs are expensive, they are hungry for data, and they need to be fed data at a rate which is definitely driven by NVMe, but also high performance fabric. So I ask all of you guys who kind of look at future deployments to not make storage and access to storage from these expensive compute elements afterthought. And let's take a kind of little bit deeper dive. And I think Ajay spoke a lot about this. So I'm going to keep my section short about this. But the point I want to make is that while Ajay talked about this machine learning workflow, which starts with the ingestion of data, which basically data coming into these data lakes that eventually will be the feeding ground that goes into the training process. Often the data kind of ingest part is definitely very capacity intensive. Data is coming in from multiple different sources, has to be moved around, and more often than not, it's a bad word to use, but the data is dirty, right? And it needs to be cleaned. There are holes in the data. Not everything looks good and clean, and a lot of people kind of work within these technology companies to write code that actually kind of cleans up that data, which is again very capacity, very IO centric. And you'll really like it when Ramya and Ashish probably come back on after I'm done with my piece. We'll talk about that when they did this actual kind of performance analysis, they were able to see the kind of proportion and direction of I/O, what was the mix between reads and writes, to give you some perspective on how storage intensive some of these phases can be. And so kind of wait for that. That's coming up right after I'm done here. But the data ingest and cleaning, like I said, very capacity intensive process. And then there's this cleaning and tagging to make sure that data is clean. It's like getting all your paperwork in order. Very cleanup is typically kind of very write intensive because you're doing a lot of things. So you need kind of storage that can respond to kind of both capacity as well as high performance writes. And then comes this big long running process of kind of training and validation, very resource intensive, right? And probably the most challenging in terms of, because this not only needs high throughput to kind of feed the GPUs, that $500 an hour lawyer sitting in the lobby, right? But also low latency and very challenging, and you need kind of specialized high performance storage to get to that. But just remember that this does not end here, right? This is just the model, and that it needs to be kind of moved around to another place and used for inferencing, right? And as these models become iterative, they grow in number and across different use cases, there is a whole lot of investment that needs to be done to kind of categorize these models, store them, reference them. In fact, I was reading up somewhere that one of the biggest challenges of machine learning has been kind of just protecting and managing the amount of data that these models spit out. So a very challenging process. The point that I want to make here is that whether it is the accumulation of data, the pre-processing, modeling or inferencing, storage plays a huge role in that. And the success of your kind of architecture depends on whether you can provide an efficient storage fabric, efficient storage mechanism that can respond to high performance writes, reads, low latency, and scale, right, as well as provide you options to start small and then kind of grow from there, which is both scalability in terms of size as well as in terms of performance, right? Often, if you kind of, just one more thing on this side, often you think about it, right? A lot of the kind of deep learning experiments begin in a bunch of different fronts, right? There's always that data scientist who needs a little bit slice of the GPU and a small slice of the storage to do some kind of models and kind of adjusting the weights and things like that, while at the same time data analysts and data engineers, they work on the instrumenting and digesting of the data, and all of this then comes together and then works on an iterative process. Storage is a key element, and all this team wants to share the same storage because end of the day they are working on a common goal, and that can be delivered by using kind of shared storage all through the life cycle of this process. Well, enough on that. Let's just, I think I have two more slides here, so hang on with me before we get to the real cool stuff with Ramya and Ashish again. But so when you think about storage, right, from a machine learning perspective, the number one reason it is important is because the time taken to train a model, right, is the one biggest challenge in machine learning. That's why all the investments are made. That's where all the kind of research work is going on. How can we do this thing faster and faster, right? And again, in the experiment that the HPE team does, they've clearly shown, how you can increase the training speed. But remember that increasing the training speed is also a function of highly dependable storage. You don't want to start a 2-week modeling run, right, and find out a week and a half later that there was this problem with storage that your local nodes could not handle, where you have captive storage and you need to rewind time again and do it. And try explaining that to somebody, to your boss, right? It can be pretty challenging. So the storage has to be robust. There's this cost efficiency of storage. Definitely, all GPUs are pricey and NVMe is pricey, and you need efficient scale out storage. And I didn't make a point earlier about containers, while Ashish talked about all the value that containers bring to the table. The reason why kind of containers are so important, as well as Not just efficient but also important is portability, right? It's about interoperability. It's no longer that machine learning or it's for that matter inferencing workloads, both training and inferencing workloads, they're not captive to the data center. In fact, there's some statistics say that like over 50% of the training actually happens in the cloud, which actually also means that 50%, the other 50% is actually happening on-prem. And there's this kind of constant portability required of software into these containers that can sometimes run on TPU running in GCP or sometimes run on-prem on GPUs. And you need the portability, and that portability and that scale can only be driven by containers, as Ashish talked about that. And I talked about kind of scalability, the need when you have like millions and billions of kind of pieces to store a typical kind of file, and many other kind of low-end storage solutions just do not match up. And that's where kind of Fibre Channel brings some excellent, proven efficiency, dependable storage, as well as reliability. Like many of us who have known Fibre Channel, it is the most reliable thing that at least I have known in my kind of 3 decades of storage career here. So definitely. And then we talked about kind of data locality, how from data analysts to data engineers, everybody kind of needs access to shared storage. And so moving on, let's take shared storage and try to expand it a little bit. Right? When we talk about shared storage, there is a couple of different kind of shared storage architectures that are possible for customers to deploy, and all kind of depends on where you are and in what stage and what your kind of desired outcomes are of your machine learning workloads. But there's definitely the shared storage or SAN model, which is traditionally Fibre Channel, and although it can be some of the Ethernet-based fabric, but it's traditionally kind of Fibre Channel. And the new avatar of Fibre Channel called FCNVMe, and there's kind of more details on FCNVMe coming up shortly. Very interesting protocol, already into its next generation, providing extraordinary high reliability with FCNVMe v2. So there's this kind of SAN architecture, SAN A and SAN B, very reliable, high performance. When it comes to disaggregating storage and sharing storage across a bunch of different machine learning nodes, this is kind of and should be the most popular choice as kind of deep learning workloads become more scalable and more broader. Then there is other kind of typical Ethernet-based architectures, which is either captive storage in each of the nodes and clustered together by some kind of Ethernet-based fabric. It could be software-defined storage. Some, especially small-scale workloads, talking about the JBOF concept here, especially some kind of small-scale machine learning workload, they could benefit from extending their DAS by kind of hanging off a EBOF or a JBOF connected over an Ethernet NVMe, typically NVMe or RDMA fabric. But basically the point I want to make is that, in this slide, is that if you're looking for the scale, if you're looking for efficiency, if you're looking for reliability, right, and if you're looking to bring the decades of experience of managing storage, right, tiering storage, compressing storage, right, bringing all the storage value, right, for machine learning workloads, then Fibre Channel and its new avatar FCNVMe makes a great choice. And this is not just kind of me saying it, as other people here from HPE show up. They'll tell you about what makes FCNVMe so efficient, and then what their own research and hands-on analysis has shown. So with that, let me pass the baton here over to Ramya. So please, Ramya, the stage is yours.
Yeah, thanks, Nishant. Is there an echo? Okay, fine. Yeah. So thanks, Nishant, and hello, everyone. Ashish, Ajay, and Nishant spoke about containers, machine learning, the storage aspects for machine learning. So what I would talk about is about FC-NVMe. So I'll basically talk first about the basic architecture of what FC-NVMe is, and its advantages with respect to ML workloads. So with that, let's start. So to give an introduction, NVMe over Fibre Channel is an architecture which is used to access the NVMe storage over the fabric. So when we talk about FC-NVMe, there are few terminologies that we normally use, as you see in this slide. So we have the target, which is the storage controller. Then we have the NVMe host, which is the initiator. Then we have NVMe namespace, which is nothing but a pool of non-volatile memory that can be partitioned into logical blocks, and the controller uses a unique identifier for these namespaces called as namespace ID to provide access. Then we have queues, which is nothing but a buffer that holds the NVMe commands and responses. Talking about queue, it is usually a set of two queues called as queue pair, uh, submission queue and the completion queue, one for sending the commands from initiator to target, and the other one is the response from the target to initiator. And then coming to queues, there are specifically two types of queues: the admin queue, as you all know, which is used to send the administrative commands, and then the IO queues, which is to submit the IO commands, basically read, write, etc. Now, as you can see in this diagram, we have depicted there's a NVMe target, which has the NVMe SSDs at the back end connecting to a server over a fabric, which supports both the SCSI and the NVMe protocol. So let's talk about how exactly a discovery process happens and how the initiator establishes the connection with the target. So normally in the when we talk in FC-NVMe, the initiator sends a discovery message to the NVMe subsystem to obtain the information about the available controllers and the subsystems on the network. And once it gets that information, the initiator creates an association first to create the admin queue, and then once it discovers the devices in the subsystem, what it does is it sends the connect command, where the initiator and the target exchange the parameters, like it could be the MTU size, could be the number of queue pairs, the size of the queues. So once that is done, it has to then create the IO queue. Admin queue is created. Now the turn is to create the IO queue to communicate with the target, because that's where the data is transferred between the initiator and the target. And as I said before, right, the submission, the completion queue, each IO queue has a pair of these queues. So once the admin queue is created, the initiator then sends the connection to the target with the queue ID and various parameters like the queue size, and the target responds back with the connection ID. This is where it is for the identification of the queues. And then is where the IO queue is created, and the initiator can then send the commands to the target devices for any kind of IO operations. So this is basically how an establishment of connection happens between an initiator and the target when we talk about FC-NVMe. So before I talk about the advantages of FC-NVMe for ML, let's talk about a few of the potential use cases normally when we talk about FC-NVMe. The potential use cases could be it could be a database, because it significantly improves the database performance by the increasing the data transfer rate, processing more transactions, and thereby improving the efficiency. It is used in virtualization, cloud computing, and yes, as you see here, it is also used for machine learning workloads, because it helps in processing the large data sets. Now, talking about some of the key features of FC-NVMe, is it enables the faster access between the storage and the host. It takes less processing time. It is lighter than SCSI and has a leaner driver stack, which allows it to run faster while consuming fewer resources. It's a multi-queue model and has built-in multi-pathing capabilities that helps to improve the fault tolerance. I said it supports multiple queues. It can support up to 64K queues. Each queue can support up to 64K commands. So this is the best performance and latency storage option that is available in today's time. Then it uses lower CPU cycles. So most of the NVMe fiber channel offloads the tasks from the server CPU to the HPA, thereby improving the efficiency. Then it is reliable and compatibility. Since we use the same existing infrastructure to support both FC and NVMe, it gives an opportunity for organizations to gradually transition to NVMe without any additional cost. So, coming to advantages specifically of FCNVMe for machine learning, users anticipate faster response time in today's world when applications become complicated and resource intensive, especially in machine learning, where it is large, complex, and changing. Machine learning data sets are large, and hence the task to process these massive volumes require a lot of GPU. It swarms the GPU local RAM, resulting in bottlenecks. So NVMe over Fiber Channel helps here because it virtualizes the resources across the high-speed network, making it ideal for AI and ML applications. It gives GPUs direct access to an elastic pool of NVMe and their support high workloads. So it also supports multipathing, which is useful for redundancy and load balancing. Thus, NVMe protocol meets the dynamic needs of storage environments for high performance workloads. And that is what we say that it's a key value proposition when it comes to serving ML workloads. And this is what will drive the future storage industry and add value to the businesses by enabling faster data access. So now that we have spoken about the advantages of FC-NVMe for ML, we would now talk about our proposed solutions, which kind of ties everything together. And before we talk about what were the numbers, I would hand it over to Ashish to first give the details about proposed solution. So over to you, Ashish.
Thanks, Ramya. Okay. Here are some of the details on our proposed solution, which are given here. The server used is x86 based architecture and a dual Intel Xenon processor running at 2.4 gigahertz with 64 gig of RAM with SAS and NVMe drives. Uh, the NVMe capable storage network infrastructure. The storage controller uses PCIe Gen 3 and supports end-to-end NVMe. Uh, Example, NVMe based flash drives, SSDs, and volume mapped over NVMe over FC. Linux operating system OS on the server that provides support for NVMe over Fabric. Uh, and both the servers and storage system are configured with Gen 6 FC 32 gig HBAs. So the steps what we followed are like, firstly we build the ML model based on our requirement. Then we created the requirement file containing all the required Python libraries. uh, the next step is to create the Docker file with the necessary environment setup, and then build the Docker image with all of its dependencies along with the YAML file for container deployment. We used HP Proliant Gen 10 server with Linux operating system and Docker, which was connected to a storage controller with PCIe Gen 3 and supports end-to-end NVMe. The storage controller had Samsung MLC SSD drives, each with 2 TB capacity. The NVMe volume mapped from the storage to the host is used to deploy the container. The Docker image can be used to create single or multiple containers that includes the required ML app and all of its dependencies, and then perform on the fly data preparation, data building, and data training. The models or data that have been trained during this process are saved on the NVMe volume that is mapped to the server, And when the ML modeling is finished, the container can be easily destroyed or re-triggered as needed. So with this, I'm handing over to Ramya to cover performance evolution with NVMe over FC.
Looks like Ramya is on mute.
Okay, yeah, I'm sorry, I was talking on mute.
Please.
Yeah. So, as a baseline for this performance characterization, what we did is we evaluated the performance of an ML model between a virtual machine and a container using FCP. And as we learned earlier in our previous slides, containers have lower overhead than virtual machines. So we did see a better performance with containers in comparison to a VM. Then the next step was to go ahead with our proposed solution where we did the performance evaluation between a virtual machine and a container, but using end-to-end NVMe this time, which means NVMe drives at the back end and volumes mapped with NVMe over fiber channel. So the VMs and the containers were deployed on an x86 server, and the volumes were mapped from the storage controller. And we ran this evaluation for a variety of training data set sizes, and the times were captured. The data set size varied somewhere between 887 MB and 35 GB. And when we talk about ML model and the reads and writes, the reads and writes happen in a different percentage in different phases. Example, like during data gathering, it involves more of reading because it has to load the training data set into the memory. Then we have the training model phase where we do a pre-processing. That's where we see that there are more reads than writes. Approximately, you can say 70% of read and 30% of write. Post training the model where the writing actually happens, that is where we see majority of writes, up to 90% of write and 10% of read. So the exact percentage of read and write again depends upon your model, ML model, and the implementation. So we discovered with this is the container's performance had advantage over virtual machine. And as you can see in this line graph, the performance improvement ranged somewhere between 17% to 54%. And this is just a sample data set, but in actual data scenario, real-time scenario, there would be huge tons of data, and you can see much better performance when you use containers using end-to-end NVMe. So irrespective of the different phases, we will see a performance gain with this container-based solution when we use NVMe over fiber channel. So with this, I would go to the last slide, which is summarizing of what we spoke till now. So as an overview and summary is shared storage architecture provides reliable and efficient mechanism for DL workflows. Fiber channel is the number one choice for mission critical workloads accessing shared storage. NVMe over fiber channel reduces the training time for container ML workloads. Robust reliability, performance, and full offload makes FC an ideal choice for ML. So with this, I would hand it over to Rupin.
Thank you, Ramya and team. Great presentation. A few points I'd like to cover, but the first thing that I'd like to request folks is to ask some questions on the webcast if there are any. I have a couple of here in front of me, so I'm just before we talk about what we want you to do after the webcast, let me post one question to you, Ramya and team. The question is, what was the type of data and algorithm being used in the suggested solution? And does the machine learning algorithm depend on the type of data?
Yeah, I can take this up. Uh, so we here we've used around tens of GBs, like Ramya mentioned, tens of GBs of textual unstructured data as our training data set, and this was collected from our internal database. On this, we removed all the symbols, the spaces, punctuation, etc., and did some cleaning and pre-processing, and ran the modeling over our cleaned data. We had a couple of rounds of data cleaning and pre-processing, and after this we used two major modeling algorithms, the first being the word to vector algorithm, and which was followed by the TF-IDF model. So these were the two major modeling algorithms that we've used. Basically, yeah, we these gave us the best accuracy in several of the natural language and processing algorithms that we did try. Coming to, does the algorithm depend on the data type? Yes, for sure. The machine learning algorithm depends on what type of data and what type of result we are looking for. So, since we had textual data, we've gone with NLP algorithms. Similarly, if we probably had image or streaming data, we would have probably used fuzzy logic or some other algorithm like that. So,
Okay, great. That's great. One follow-up here. Will the performance improvement be the same regardless of the training data type?
yes, as definitely that's what is expected, and that's what's been seen as well. As we expect, the performance improvement is seen the same regardless of the data type. The percentage, as we saw, might vary slightly, but the improvement is still significant.
Got it. Got it. So directionally, you see advantages in performance. That's great. We have one more question on the web now. Did you use point-to-point connections for your fiber channel network, or did you use switches?
We use switches, and the switches were the ones that were capable of handling NVMe over fiber channel. So it was not a point to point.
Perfect. Perfect. Great. Well, one more question. Are there any limitations of containers when you're using these machine learning type of workloads?
I will take this up. So container actually don't have any specific limitation for ML. However, if you talk about containers in general limitation, right, then the first is containers can introduce security vulnerabilities if not properly secured, or if the container image is not updated regularly with the latest security patches, then it may be vulnerable to attacks. And the second is the complexity. Sometimes people may find it difficult to adopt containerized ML models, since they are very complex to set up and manage, and require specialized skills.
Okay. Okay. Great. Yeah, absolutely. Security is top of mind. Hey,
Can I?
I don't have any more questions, so thank you for all those answers. Before we end the call, I'm sorry, somebody has something?
Hey, Rupin, I just wanted to add to that kind of container
Yeah, please,
question,
please.
right?
Nishant. Yeah.
See, there is, and this is more of a myth, right? A lot of people think that enabling persistent storage for containers, delivered by the runtime Docker and managed by Kubernetes is challenging, right? But I'll tell you, at least in my experience and my visibility, it is not. It used to be a problem many years ago, where but today with I think there are kind of CSI plugins from all major storage vendors that enable you to deliver persistent storage to containers seamlessly. And that is also kind of one of the enablers of bringing external storage to containers running machine learning workloads, and bring all that value into containers. So sorry for interjecting, Rupin, but I wanted to add that.
Okay, no, no worries. Thank you so much. There's one more question. What type of fiber channel switches were used, and did you try different types of switches?
For this, we have used the brocade switches. We have in the past we have for the same experiment we have used Cisco, but for specifically for this webcast we have used brocade switches.
Got it, got it. So basically, this type of you can use Brocade or MDS, Cisco MDS.
Yes,
Okay,
yes.
great. Okay, this is great. Thank you, guys. I'm not seeing any more questions coming in, so please rate this event. We really value your feedback. I would appreciate if you can take just a minute to rate it. We will definitely post a Q&A blog for this particular webcast on fibrechannel.org. Please follow us on Twitter. And also, if you want to go back and watch our webcast, we have a nice library now available. The link is up there. And by the way, FYI, we see that 2 to 3 times more views of recordings versus what we see people showing up for the live presentation. So, this is something that we are noticing a ton of interest in, and people continue to come back to our webcast and learn about Fibre Channel and storage technologies. So with that, thank you, everyone. This will bring end to our webcast. Thanks for joining. Bye-bye.
Thanks, everyone.